Good morning, class. Today's Wednesday, June 3rd, 2020. Coronachem day 42, period 4. We're starting with the homework I assigned yesterday from practice example on page 648.
The question is as follows. At 500 Kelvin, the reaction of PCl5 gas turning into PCl3 gas plus Cl2 gas has a Kp of 0.497. In an equilibrium mixture at 500 Kelvin, the partial pressure of PCl5 is 0.86 atmospheres and that of PCl3 is 0.35 atmospheres. What is the partial pressure of chlorine gas in the equilibrium mixture?
This question is easily answered by setting up a small algebraic equation. Let X equal the concentration of the chlorine gas, or the partial pressure, in atmospheres. Here's the equilibrium constant displayed as products over reactants. So these two are the products, here's the reactant, and the concentrations are 0.35, X, and 0.86. So we're solving for X, and it's quickly solved on all of it, obviously equals 0.497, and we get X is equal to 1.22 atmospheres. That would be just about the easiest kind of problem I could give you using equilibria. Now let's do one where we actually have to substitute the variable and solve for the equilibrium concentrations using the quadratic formula the same way we've used it for acid-base problems. This is the practice example on page 649. So it's the same setup with the same reaction, PCl5 gas reacting to form PCl3 gas and chlorine gas. But now the and also the Kp is 0.497.
Now they ask you to start with an initial pressure of 1.66 atmospheres
of the PCl5. So a nice table is going to be useful for solving all the equilibrium concentrations. Initially there's 0 of the products. Let X equal the amount of PCl5 gas that reacts, so that at equilibrium the pressure of the PCl5 gas is going to be 1.66 minus X. So whatever amount of PCl5 disappears, the same amounts of PCl3 and Cl2 will appear. So we're going to put plus X for that, and at equilibrium it will be X. So the Kp value portrays this equilibrium, and we can substitute the algebraic equivalence. X times X over 1.66 minus X, all of it equal to 0.497. When we solve the quadratic formula, because of trinomial results, we'll get X squared plus 0.497. I'm just going to skip over all the arithmetic in the middle because it's going to clutter our board. So I used the quadratic formula. I obtained a value of X that was 0.6931858. That's what I got in my calculator readout. So that means it equals the PCl3 concentration, or partial pressure, and the chlorine gas partial pressure. And the PCl5 partial pressure will be 1.66 minus X, which equals 0.967 atmospheres after sig figs. I forgot to put the sig figs here. You're only allowed 3 sig figs, so it's 0.693 atmospheres for both of those two substances, PCl3 and Cl2. So that's the problem solved using the quadratic formula when necessary. The next concept I want to bring up is LeChatelier's principle. Now, LeChatelier's principle is found on page 649 of chapter 4 and 15. I'm going to read you what I wrote. So it's an abstract from the textbook, but you should read the whole chapter yourself, and especially this part. So LeChatelier's principle: a system at equilibrium that is disturbed by a change in temperature, pressure, or concentration of one of the components will shift its equilibrium position so as to counteract the effect of the disturbance. So the equilibrium shifts to counteract the effects of the disturbance. So supposing, using LeChatelier's principle, if I was to take away the chlorine gas as it formed, the equilibrium would continue to shift in that direction to produce more chlorine gas. That's what LeChatelier's principle is saying. LeChatelier's principle was exploited, or perhaps discovered, when Germany tried to make ammonia so that they could make explosives in response to an embargo, because during World War I, they were selling guano, which is bird droppings, to Germany from an island somewhere in the South Atlantic, I believe, off the coast of some South American country. I can't remember if it was the South Pacific or South Atlantic. Anyway, it was an island that was inhabited by many birds for thousands of years, so they had literally mountains of guano, which is very rich in nitrogen, can be used, the nitrogen can be extracted to make bombs. When Germany entered the war, they were no longer sold any of this guano, so they couldn't make explosives using that source of nitrogen. So what they did is they set to work to find a way to make ammonia using gases that were readily available from the atmosphere, nitrogen and hydrogen. And they inadvertently solved world hunger. They were attempting to make explosives, but they also solved world hunger, because one of the problems with intensive crops is that it depletes the soil after a while. So what farmers have to do now, modern farmers will add ammonia to the soil to replenish the soils so that the crops can continue to be plentiful. So the goal was to find explosives to blow up the enemy, but they also at the same time discovered a way of replenishing soils. So, the Lord works in mysterious ways. Let's look at how LeChatelier's principle is applied. This is on page 651. What happens to the equilibrium? I'll give it some thought. It says, what happens to the equilibrium 2NO gas plus O2 gas turns into 2NO2 gas if A, O2 is added to the system? Well, adding more reactants will tend to shift the reaction in the direction that will reduce the reactants back to the equilibrium position, assuming the reaction is already at equilibrium. So it'll move the reaction to the right. And what if NO is removed? Well, if you remove NO, because NO is on the left side of the reaction will shift to the left to replace the NO that has been removed. On the next page, on page 652, it says, give it some thought. What happens to the equilibrium 2SO2 gas plus O2 gas if the volume of the system is increased? Let me write this one down because you might find it hard to follow. So SO2, this is this is give it some thought on page 652. And it shows LeChatelier's principle in action. 2SO2 gas plus O2 gas is turning into 2SO2 gas. So if you increase the volume of the system, you create more room for the gas molecules to occupy. There's 3 moles of gas on this side, there's only 2 moles of gas on this side. So if you create volume, you're going to encourage the reaction to shift left to create more molecules to fill the lowering of the pressure or the increased amount of volume. So it would move the reaction to the left.
And also thing you might want to keep track of, adding an inert gas to the mixture will increase pressure, but without altering partial pressures. This would not cause a shift in equilibrium. So there's a little trick question there. When they add inert gas, it has no effect. Heat. In an exothermic reaction, heat may be viewed as a product.
So let's say you have A plus B reacting and it produces C plus D plus some heat. This would be an exothermic reaction. If you had the opposite, say you had heat and then A plus B turning into C plus D, that would be an endothermic reaction, and the heat would be a reactant. So it's a good way to look at it because it'll help you understand the movement of the equilibrium when a reaction that is endothermic is heated. So if you heat an endothermic reaction, it tends to drive it left. And if you heat, if you heat an exothermic reaction, it tends to drive it left. If you heat an endothermic reaction, it tends to drive it right. Catalysts increase the rate at which equilibrium is attained, but does not change the composition of the equilibrium mixture. So the equilibrium remains the same, the catalyst just brings you there faster.
And I wanted to do an example with you. For the reaction PCl, this is on page 655.
I'm going to apply LeChatelier's principle now. So practice example on page 655.
This marker is beginning to hesitate. Doesn't write well, so I'm going to get a new one.
Here's the reaction, PCl5 turning into PCl3 plus Cl2 gas. Now what's going to happen if A, Cl2 is removed? So you take away Cl2, moves the reaction to the right to refurnish Cl2. B, the temperature is decreased. Now, I forgot to put the delta H equals 87.9. This is an endothermic reaction. So the temperature is decreased in an endothermic reaction. You're taking away heat energy. It's like taking away the heat on this side. The reaction is going to shift to the left. C. The volume of the reaction system is increased. You increase the volume, you have 1 mole of gas turning into 2 moles of gas. It doesn't matter what the gas looks like. Remember that according to Avogadro's law, equal number of molecules occupy the same amount of volume. So in this case, all you're looking at is the number of moles of gas. Here you have 1 mole of gas, here you have 2 moles of gas. If you increase the volume, then the reaction has available more space, so it's going to create more molecules, and that means it's going to shift right. Then the last one, PCl3 gas is added. If you add more of this is the product, it'll shift it to the left to re-establish the concentration of the PCl3, assuming the reaction is already at equilibrium. The next thing I want to do with you is the example on page, well, never mind the page, example number 1551, which is, again, following LeChatelier's principle. Actually, you know what? We just did that. We just did one like that. I'm going to skip that over. We'll do the next one. The next one that I wanted to do was 1552 will be your homework, okay? So here's your homework. 1552. The other one that I want to do with you, because it's kind of tricky, is 1567.
because when I did it the first time myself, I tried to approach it from the point of view starting with KC, and it didn't work. I tried to set up an ice table, and it didn't work because the variables were up to the 4th power. So calculators will solve up to the 3rd power. You can do quadratic equations or cubic equations, but if you go to the 4th power, calculator won't do it. And basically, you're asking for trouble because there's an easier way to do it. So I went and I solved it from the point of pressures, partial pressures. So 1567.
So we'll start off by saying that you want to know the pressure of the gas before it starts reacting, because we're doing it on the basis of partial pressure. So P equals nRT. All they tell us in the question is the mass of gas available. So let's read the question. A 0.831 gram sample of sulfur trioxide is placed in a 1 liter container and heated to 1100 Kelvin. The sulfur trioxide decomposes to sulfur dioxide and oxygen. They show you the reaction. At equilibrium, the total pressure in the container is 1.3 atmospheres. Find the values of Kp and Kc for this reaction at 1100 Kelvin. So we're going to work with Kp, but to work with Kp, you got to turn 0.831 grams of sulfur trioxide into moles of sulfur trioxide, so you can then put it into the P equals nRT. So 0.831 grams divided by the molar mass of sulfur, which is 32.066, plus 3 times the molar mass of oxygen, which is 15.394 grams per mole. That gives you 1.037917 072 times 10 to the minus 2 moles of sulfur trioxide. Then, 2 moles of the gas turns into 3 moles of the gas, but don't worry about that because we're going to set up an ice table anyway and solve it that way. Okay, so using P equals nRT, we're going to solve for the pressure. And therefore, pressure is equal to nRT divided by V. Plug in all the values. So for N, it's this number. I'm not going to write it all over again because it's going to take up all my room. R is 0.082057 liter atmospheres per Kelvin mole. And the temperature is 1100 Kelvin. The volume is 1 liter. So the pressure from that turns out to be 0.936,851,9729. We're going to use all the numbers while we're doing the calculation. After, when we round off and present our final answer, we will put the appropriate number of significant figures. Now, this is before reacting. So let's portray the reaction. 2SO3 gas is turning into 2SO2 gas plus O2 gas. And let's set up an ice table. You have the 0.9368 blah blah blah. I'm not going to write the whole number again. A certain amount X will be reacted, which means at equilibrium you're going to have 0.9368 etc. minus X. This will be 0 initially, and plus X will appear, same stoichiometry, 2 to 2. So X at equilibrium. This has a 2 to 1 stoichiometry, so it starts off at 0 and it increases by 1/2 X, and it will be 1/2 X at equilibrium. So when we set up a trinomial where we say that Kp, in this case, is the sulfur dioxide concentration squared times the O2 concentration over SO3 concentration squared, we get the following. We don't even get a trinomial. total pressure because they give you a total pressure at the end. You don't have to do it, you don't have to solve it in terms of, because they don't give you Kp, they're asking you to calculate Kp. What they do tell you is that the pressure of this gas plus this gas plus this gas at equilibrium has to equal 1.3. So all these numbers together, let's put a plus sign there because we're running out of room, has to equal 1.3 atmospheres. So that means if you solve for x, you get that 1/2 x is equal to 0.363148 028, and that means that x therefore equals 0.726 296 056. So now we can use the values of x to solve for the equilibrium concentrations of all those gases, plug them into the equilibrium equation here, which means I have to erase, or else there's no place to write. Maybe I should have bought 2 of these boards. Hope this does not continue in September. If this continues in September, I'm going to drive a truck instead. (1567) continued. So Kp is equal to pressure of SO2. I forgot to put pressure in the equilibrium constant. Same numbers on me. It's just me being sloppy. So plug in the numbers now. You get 0.726, etc. raised to the power of 2. 0.363, etc., and 0.21055 squared. So I'm just subtracting the x from the numbers I had in my ICE table to get all these numbers, in case you're wondering, and you get a Kp value equal to 4.320854.005, and you report it as 4.32 after sig figs. Now, we also know that Kp is equal to Kc times RT to the delta N, where delta N in this case is equal to 3 moles of product minus 2 moles of reactants. So the delta N is going to be equal to 1. So we'll take the value of Kp, which is of, well, first let's isolate it to get Kc by itself. So Kp over RT to the power of 1 is going to give you the Kc. So 4.3208, etc. over 0.08201, 02057, sorry, liter atmospheres per Kelvin mole, times the temperature, which is 1100 Kelvin. And what we get is, after sig figs, we get 4.79 times 10 to the minus 2. And that's the final answer for Kc. So Kp equals 4.32, Kc equals 4.79 times 10 to the minus 2. So that was a kind of tricky problem, but I found it enjoyable. So for your homework, I said 1551. No, I said 1552. So your homework then is going to be 1552. And let's get a nice juicy one for you. Let's try. Oh no, the next one. The next one needs a graphing calculator to be solved. I redid it. Oh, it said. You know what I did for 1568? No, I'm not going to give you that one. I answered the question. I answered a question that it wasn't asking. That's why I ended up needing a graphing calculator. Then I reread the question more carefully, and it said I only had to predict the behavior. So I only had to predict whether the reaction goes left or right, not to give the final exact number. So I did 1568 wrong. I'll give you 1569.
No, better. 1572.
Try that one. Okay? Try these two for homework. Tomorrow we'll review them together. And I will see you tomorrow.